Hey there, chemists. In this lesson, we're going to look at how we synthesize amines in the laboratory. Amines are also called alkaloids if you have a naturally occurring amine. And on your screen are just some examples of successful drug molecules over the years, anything from the anti-malarial quinine to one of the first successful antidepressants in the 80s known as Prozac, along with some other, drug molecules that are perhaps known to the audience listeners, but that's why I call this slide amines good and bad. Currently, there's, tens of millions of chemical abstract service molecules that are classified as organic entries, and many of them that are biologically active fall into the alkaloid category. So knowing how to make an amine is very useful for a medicinal chemist if we want to make good drug molecules. So we're going to look at how we make them. Today, we're going to focus on what's called reductive amination. This lets us make a variety of amines from a functional group called an imine, spelled almost exactly the same, but it starts with an I instead of an A. And that comes from ketones and aldehydes. So if I look at a carbon-nitrogen bond, I can think about making it from a carbon-oxygen bond via the imine. That's what we're going to see today. And it's a very useful reaction to turn carbonyls into amines. I'll show one way of doing it just with acid-catalyzed chemistry. This is how we can make the imine. We'll start with just that. And you have to bring in the nitrogen molecule as a small amine. So here we have methylamine. In the presence of acid, that will make the imine and a water molecule if you balance this. This is acid catalyzed, so we're only going to see positive charges in our mechanism. And our first step is to protonate our ketone and give us that familiar oxonium that we saw back in the days of acetal and ketal chemistry. Then the oxonium, which has an H plus on it, will see the amine. The amine is a nucleophile on the nitrogen. It will form a bond with that carbonyl carbon, send that pi bond up to the oxygen, and that's how you form your nitrogen-carbon bond. Everything else is along for the ride. Notice the plus charge is no longer going to be on the oxygen. It's now going to be on the nitrogen. So to check in with where we are versus where we want to go, we have to spit out a water molecule and create an extra pi bond. You can't lose the hydroxyl as is, so we need to turn that into a water molecule. We'll do an acid-base reaction, and I'll show it in one step like we've done a couple of times now, as if it happens intramolecularly. Remember, in all likelihood, this happens intermolecularly, probably with a solvent or another equivalent of one of the reactants. But in the end, you get one less hydrogen on the nitrogen and one more on the oxygen. And even though it's reversible, this gets us where we want to go. Now the water molecule can leave. You'll get a carbocation in its wake on that carbon. And that's a great cation because the nitrogen has a lone pair that can donate and form that double bond. Remember, these are just two different contributors of one compound stabilized by resonance. You could actually show this arrow, since it's a resonance arrow, on top of the original intermediate. That would get you straight to this contributor, which one could argue is more significant because it satisfies the octet. This actually has a name as well. This is called an aminium. It's essentially a positively charged imine. And to get to the imine, we simply need to lose that last H. I'll use the water that just left. We could also use the starting amine. But if we use a water molecule to take that H away, it puts that electron pair back on the nitrogen, and that's how you get your imine. So notice we have a first step of putting an H plus on and a last step of taking an H plus off. That is very commonly seen in any acid-mediated reaction. So that's just how we make an imine. How do we turn this into the amine, into the carbon-nitrogen single bond? There's three different ways that I'll share that break it down into making primary amines, secondary amines, and tertiary amines. And they all come from similar functional groups, but they're not exactly the same. A primary amine can be made from what's called an oxime. And that's if you have a ketone and you react it with what's called hydroxyl amine. It's sort of a masked equivalent of ammonia, but it's a solid, so it's really easy to work with in the laboratory compared to gaseous ammonia. The mechanism for the formation of this oxime is essentially the same as what we saw up above. You lose water. These are also called condensations as a result. Oximes are also very stable. They're H-bonders, so they're usually solids themselves. And oximes can be reduced with lithium aluminum hydride. And I'm not going to do the whole mechanism for this, but this is how you can get a primary amine. When we say primary amine, that designation means the nitrogen is attached to one other carbon, and then the other two spots in this case are hydrogens. What if I want a secondary amine? A secondary amine would actually come from something like what we just made, an imine. And you can make an imine from a ketone. We just showed that. Now, I could reduce an imine with a reducing agent like LAH, but once you get to things that look like imines, there are milder reducing agents out there that work, such as sodium triacetoxyborohydride, which has this formula, NaBH, and then 3 acetates. This still acts as a reducing agent, but it has the benefit of not reducing aldehydes and ketones. So I can get a secondary amine specifically from the imine, which is reversibly formed from the ketone. So luckily, things like NaBHOAC3 do not reduce ketones. So I'll selectively go for the imine as opposed to the ketone. Similarly, we can do the same kind of thing for a tertiary amine. You can start with a ketone, and you could react it. Well, I didn't even show the reagents for this back here. That would be a primary amine. Here we could use a secondary amine, R2NH. And what you get with a secondary amine is actually the aminium we saw in the mechanism at the top. And aminiums can get reduced just like amines. And we could actually use the same reagent. There's another one I'll show here, NaBH3CN, sodium cyanoborohydride. That will give you a tertiary amine. So those are 3 examples of ways that give us primary, secondary, and tertiary amines. Remember, the designation primary, secondary, tertiary refers to how many carbons attached to the nitrogen. Formation of the iminium is also reversible. We'll go ahead and put that there. I didn't show the mechanism for any of these, but you could imagine how it works. If I zoom back in on the iminium, each of these acts as a source of hydride. This sodium cyanoborohydride is essentially a hydride source. So that's how I think of it behaving, which means it can attack the iminium, send that pi bond up to the nitrogen. Well, actually, in one shot, that's how you get your tertiary amine. Similar types of arrow pushing could be done for the imine. It's a little bit more complicated for the oxime, but in the end, you get that extra hydrogen on the carbon that's attached to the nitrogen. That's the main point. So anytime we see a carbon-nitrogen single bond, we think back to it used to be a carbon-nitrogen double, which used to be a carbon-oxygen double bond when we're doing this in a synthesis. We'll just close with showing the reversibility of this. Like our acetal and ketal chemistry, the imine formation is reversible. We can actually turn it back into a ketone. Here is an imine, and we spit out a ketone and a primary amine. So what I want you to do is hit pause and see if you can figure out what the arrow pushing would look like, and then what all the intermediates would look like, in order to turn this imine back into a ketone and a water molecule, taking note that you're an acid So only positive charges, and the first step and the last step will be protonation and deprotonation. Try that now. Okay, welcome back. If you did that, your first step is going to be protonation, and there's only one thing that can protonate. It's the nitrogen of the imine. So you'll actually start by making an iminium. Then we need to make a carbon-oxygen bond. It's sort of the reverse of what we have at the very top of today's lesson. That oxygen is going to come from water. Water will attack the iminium, send the pi bond up to the nitrogen. You get a new carbon-oxygen bond. Your nitrogen no longer has a plus charge on it. Your plus charge is now on the oxygen. We need to lose a methylamine in this case. We don't have it yet, but we can if we do an H plus transfer, which again I'll just show intramolecularly instead of inter. Now I've got a methyl ammonium directly attached to that carbon. So we can have it leave. And at the same time as it leaves, I'm initially thinking about a plus charge ending up on that carbon, but I'm going to go ahead and draw the resonance contributor that's more stable and bring in that pair of electrons from the oxygen. That gets us to an oxonium. And then how do we get from this oxonium to the ketone? We can use another equivalent of water, or we could arguably use the methylamine that just left. That's certainly a better base than water. And that will get you your ketone, and you'll end up regenerating an acidic molecule, in this case methylammonium, but the net generation of something acidic still holds true. So that's how we turn an imine back into a ketone. It's the opposite of making an imine from a ketone or an aldehyde. And then the key is we can turn those carbon-nitrogen double bonds into carbon-nitrogen single bonds to make amines.